Good afternoon and welcome to Research in Action, brought to you by the Division of Research at Florida Atlantic University. My name is Karen Scapinato. I am today's moderator. It is my great pleasure to introduce today's speaker. Gabriel Alsenas is the director at Florida Atlantic University Southeast National Marine Renewable Energy Center. While he is a native of Cleveland, Ohio, Mr. Alsenas completed his undergraduate and graduate degree in Ocean and Systems Engineering at FAU and had a little hiatus in international internet consulting in the late 1990s before coming back here to FAU, and has now been serving as the director of the SNMREC Center for multiple years. In 2020, Mr. Alsenas was selected as a recipient of the IEC's 1906 award that recognizes exceptional individual achievements which help advance international electrotechnical commission activities in a significant way. And I'm going to have him just tell you all about what he's doing. As you can see, he is in the field right now, so he can tell you exactly where he is and what he's doing there. Gabe, take it away.
Thank you, Karen. Let me get the video started here. So thank you again, Karen, and thank you for the invitation to discuss our center's perspectives on how Florida can position itself as a global leader in renewables. So let's start with the basics. James Prescott Joule's first law of thermodynamics, also known as the law of conservation of energy, in summary states that energy can neither be created nor destroyed. It can only be transformed. Without the ability to transform energy from one form to another, we wouldn't have all the conveniences of our daily lives. We especially rely on the transformation of electrical energy into mechanical work or light or cooling or heating. In our ever-growing demand to power more stuff in our lives, we need to figure out how to maintain a continuous supply of available electricity as affordably as possible. This demand can and currently does come from highly energy-dense fossil fuels and nuclear power. Or it could alternatively be coming from energy directly available to us from our environment, what we call renewables. Of course, energy from these sources isn't created either. It's also transformed, leaving us the challenge to try to find ways to make the transformation more efficient, accessible, and sustainable. Let's start with two common solar-powered renewables pictured here. No, that's not a mistake. It is true. Photovoltaics and wind turbines could both be considered solar. Well, while many of us don't commonly label wind turbines this way, it could be a very fitting choice, because all the energy that we have access to, what engineers call either potential energy or stored energy, or kinetic energy, or the energy available from the movement around us, is fundamentally driven by the sun. Granted, photovoltaics are the most direct way to tap into the sun's radiation that we've so far invented, but winds on our planet are also created from the sun, indirectly from the differential heating and cooling of the Earth's surface. Even fossil fuels are stored energy from the sun millennia ago. So, if all of our useful energy is really just different forms of the sun's light and heat, where else can we look to diversify our current options? Our answer, of course, is to look to our oceans. At blue energy. Here, we can find energy stored in gradients, meaning the differences of various properties of the water, like for example, salinity, which is the salt content, or the change in water temperature with depth. We can also find energy readily available in the ocean's movement. Because the ocean is approximately 1,000 times more dense than the air, the motion of water offers a very potentially compelling alternative to harnessing the movement of the air, as wind turbines do. One obvious source might be from waves, but since Florida isn't generally known for big waves, just ask surfers, we need to find currents that are big enough and consistent enough to provide useful power to utilities that serve our communities. Flows of this magnitude are either caused by tides or are found in open ocean currents. Created primarily by the gravitational pull of the moon, tidal flows occur when water flushes into and out of constricted channels. Naturally, these are found close to shore, which makes delivering the power less costly. As tides ebb and flood with a slack in between, it also affords an opportunity, albeit short, to work in a less extreme environment. Therefore, tidal projects have been the first to be developed worldwide, and there are a couple of very successful examples in the US. The first is a company headquartered in Portland, Maine, whose first delivered power to electric utility a decade ago. This is just a sample of the milestones, that the Ocean Renewable Power Company reached. As you can see, they were the first in the US to install commercial scale turbines and to deliver electricity to an electric utility grid back in 2012. They've since adapted their technology for rivers in Alaska to power remote communities that have dependence on diesel fuel, especially its pricing and availability, as well as for other tidal areas around the world, for example, Canada, Ireland, and Chile. Also recently in the news, Verdant Power retrieved 3 turbines from the East River in New York City. This was a few weeks ago and achieved some very impressive milestones, especially despite restrictions and other challenges last year. They achieved over 99% availability and generated more than 210 megawatt hours over a full year, a new record in the US. Interestingly, neither of these companies were looking to tides as their primary targeted renewables, which brings us to what Floridians may have access to. Here in the Sunshine State, of course, we don't have large tidal flows, except for some spots in the Florida Keys. But we should still feel pretty good about some unique options a few other areas have. Mariners in Southeast Florida are of course aware of a massive current that transports 30 million cubic meters of water every second past Florida called the Gulf Stream. Western boundary currents, like the Gulf Stream, resemble giant rivers without riverbanks in the open ocean. These are driven by the winds blowing on the major ocean basins. As a consequence, they're near the surface and along our eastern coastlines of continents, of course, due to the rotation of the Earth. Here's a view of the Gulf Stream at 27 degrees north near West Palm, as if you were standing in the ocean looking north with Florida on the left and the Bahamas on the right. We could see this phenomenon in the concentrated lines or the high speeds at the surface near the Florida coast. For centuries, we've used the Gulf Stream for activities like trade, fishing, and recreation to harness it, to provide our power as well. But why would we want to do such a thing? Well, first, there's the amount of energy that's available. According to a Georgia Tech study that was completed for the US Department of Energy in 2013, the Gulf Stream and the Florida Straits could generate 45 terawatt hours per year. That's about 4 to 6 gigawatts of capacity. For scale, Turkey Point Nuclear Power Plant is about 1.4 gigawatts, and St. Lucy's nuclear power plant is about 2 gigawatts. So the Gulf Stream could realistically provide at least 2 nuclear power plants worth of power. However, there may be even more compelling reasons to harness the Gulf Stream if you're an electric utility. Because the Gulf Stream is not intermittent, like photovoltaics, wind, waves, or even tides, it offers a truly what's called baseload power generation opportunity, something not generally found with any other renewables. It also means that power can be what's called dispatchable, or in layman's terms, it's there when you need it. This ultimately means that we should be able to achieve cost parity for electricity consumers, because battery storage, sophisticated power balancing, and other technologies won't be needed. So it is possible to achieve domestic energy fuel security with renewables. So why haven't we done it? First, As many other things like this, there are high costs to overcome. Because technologies to harness ocean currents are still very nascent and unproven, there isn't a convergence of technology which leads to cost savings. Think of a 3-bladed wind turbine on a mast. Here is just a small sample of the very diverse technology approaches of companies that are looking to harness ocean currents. There are companies shown here that hail from the US, Florida, Sweden, and Japan, to show a little bit of the international interest. The company heritages also range from inventors to major original equipment manufacturers like Saab. Also, the industry has not achieved what's called economies of scale. These drive down costs. When a handful of companies only have access to custom one-off parts and no local supply chain or marine services that are set up to support a larger industry locally, costs for each installed unit become high. So for a project to make sense to investors, it must be scaled appropriately. And an ocean current turbine here or there just isn't going to cut it. We need to think bigger. Bigger than just the widgets that produce the electricity, as cool as they are, and view projects much like traditional utility projects, something like what's pictured here, with the project developers assuming the risk for the overall project, but also the lion's share of the rewards. Developers will bring together all the parts and pieces of an offshore generation project, reducing risk along the way as much as they can, by, for example, seeking certified technologies and ensuring their installations. They enter into contractual arrangements with utilities who are responsible for transmitting and distributing the electricity that's generated by the project to the consumers. And we've started to see project developers show interest and invest in starter projects to test the waters, pun intended. These lay the groundwork for larger projects. A good example of this is a Miami-based company called Ocean-Based Perpetual Energy, with whom we worked last spring to demonstrate the 24/7 power generation opportunity that the Gulf Stream offers. So we, of course, view this offshore energy development as a system of systems challenge, where the various aspects of a successful future commercial project are all interdependent, and they all need to be equally addressed. As we all know, there are a variety of uses of the ocean by both wildlife and our communities that need to be reconciled. Natural resource managers and industry must find a balance which protects the natural resources but still enables commercial development. While we believe that there is room for all to coexist, the uses need to be better understood and the potential conflicts mitigated. That's why our center and the researchers around the world are studying these aspects. Our approach to address environmental questions is to first understand the likelihood and possible risk of interaction between the equipment installed offshore and wildlife. To do so, we need to first map where the animals are throughout the year. To do this, we have performed aerial surveys to better understand marine animal distributions and their activity. Then, our focus shifted to how individual animals interact with the equipment. So, we've helped to develop highly specialized systems like the one on the right that can be installed on small-scale turbines while they're being tested to provide a continuous 3-dimensional view of the activity around them using lasers. This is also technology that can be installed on the commercial systems to monitor any of the potential interactions once they're installed. FAU was also issued the first US lease to conduct marine renewable activities on what's called the US Outer Continental Shelf, the lands here, at least in Florida, more than 3 miles offshore. And in the process, we have provided significant input from our research into the current federal framework to authorize new commercial projects, something we're very proud of. Around the world, efforts like these are helping to provide answers to many of the outstanding questions and to retire risks so that the technologies can continue to be developed. To help companies better understand how to optimize their technologies, we measure, model, and characterize the Gulf Stream as well. Since 2009, we've nearly annually installed moorings which collect the current speed and direction throughout the entire water column. An example of that equipment is shown on the left. We have also installed coastal radar stations which provide near real-time data about the sea surface's direction and speed also, for the moment, offshore Broward County. Those you see in the middle and on the right. We're also looking to expand these systems to Palm Beach County and have developed a very novel method to measure natural turbulence in the Gulf Stream, something that's very important and useful for companies to understand the reliability and lifespan of their technologies. They need to compete ultimately with land-based generation systems that often have lifespans over 20 years. So despite what might seem like very challenging obstacles, both the state of Florida and the US Department of Energy think that these kinds of projects are worth pursuing, which is why they have established and supported our center. Our role in the industry is to basically be a facilitator and an enabler, to fill the science and technology gaps, provide tools, and train the workforce, things that universities are very good at. At its core, our center's vision is to stand up a viable marine energy sector, not just individual companies. But in order to achieve this, an entire ecosystem needs to be pieced together with a combination of private, public, and academic support. These all fit together to leverage public funds, private funds, and the technology that industry creates. A new industry cluster is needed, an initiative that we call the Blue Energy Innovation Cluster. Over the past 15 years, and with more than $22 million of both public and private funds, we've worked very hard to contribute to many of the facets of the future market as possible. However, our university can't do this alone. If we are to help a new industry cluster grow, it will require strategic partnerships, both public and private. This is an area that we have especially started to focus on, especially with one of our key partners, the city of Lake Worth Beach, located in Palm Beach County, Florida. Together, we've made very good progress towards the goal of establishing a new marine energy industry cluster in Southeast Florida. Private utilities, like Florida Power and Light, rely on revenue from commercial and residential customers, those that purchase the power. Municipal utilities, on the other hand, like the city of Lake Worth Beach has, are also tied into the economic health of the area and its subsequent tax base. As a result, there may be more of an appetite to engage in cluster building and innovation for a new sector. In this city's particular case, it's a very progressive mindset, and they have several projects already underway that help to show their commitment to renewable energy and energy efficiency. So, together, we've started trying to better understand the scale of first the economic impact that might be possible. In a study that the city requested, Fishkind and Associates evaluated the potential economic impact of capital investments that will be needed. For example, the installation of onshore and offshore power cables. And for this study, they ignored that potential additional revenue that would be recovered from electricity generation. For example, that Florida Power and Light depends on. The results were very promising, with estimates of more than 500 new jobs created and an annual economic impact of $90 million annually to the whole region. This would not only quickly recover any initial capital investments, but would also position the region for strong, continued economic growth for possibly decades. We also tried to get a better understanding of how the city's municipal utility might facilitate the development of the sector by, for example, providing a key link, a key necessary ingredient, the connection to its grid. So another study was conducted by a company called 3U Technologies, a leading offshore oil and gas engineering firm, to explore just where might you be able to place turbines offshore Palm Beach County in the city of Lake Worth Beach, and then connect them back. What infrastructure would be needed? We've developed a preliminary plan, and we hope to expand on that as we move forward. Finally, together, we've been working collaboratively to try to build a combination of federal, state, and local support. These projects aren't limited to benefiting just a small community or even just our region. The state of Florida, the US, and even other parts of the world that have nearby ocean currents will all benefit. The work that we do here also significantly benefits any of the tidal projects. Many of those technologies can also be installed and tested with the infrastructure that we plan to put in place. Southeast Florida is the most ideal location in the entire world to set up a blue energy innovation cluster. Arguably, we have the best ocean current resource right off of our shores. We have world-class ports, healthy marine economies that are already established, and our communities are growing, which means they're going to need more power. As FAU's Southeast National Marine Renewable Energy Center continues to work to transform Southeast Florida into a global hub for marine energy by capturing energy from the sun in the oceans and transforming it into electricity, we look forward to working with our strategic partners, our communities, and the industry in years to come. Be very happy to answer any questions that there might be.
Thank you, Gabe. And this is a reminder to our audience, if you have any questions, please hover your mouse on the bottom of your screen. There's a Q&A button. If you push on that button, a little pop-up comes up and you can type your question there. Gabe, you mentioned that you're primarily interested in currents, and we do have the Gulf Stream here. Can you address if your technology primarily works only where we have the Gulf Stream, or is it available in other areas as well?
That's a very good question. And the short answer is that it will work in other areas. We have western boundary currents like the Gulf Stream around many other parts of the world. Any of the eastern coastlines of the continents have some sort of western boundary current that's available to them. A few examples, we have the Agulhas current in South Africa and the Kuroshio current in Japan. Both of these currents offer opportunities to install equipment. And that's one of the reasons why there are Japanese companies, for example, that have been involved in developing technology. They all have slightly different characteristics though. So here in the Florida Straits, we have the Bahamas, which constrain how wide the current can be and pack the current into one area, which is very conducive to a small project, geographically speaking, being developed. The Kuroshio and parts of the Agulhas, on the other hand, are found sometimes in deeper water and are often more widely spread out or meander, meaning the currents actually move slightly east and west throughout the year. So here in Florida, we think this is the best location to do it, but of course, it's a global marketplace. This isn't something that we're just limited to in terms of market opportunity.
So you mentioned that you're looking at the very first step are the animals. You're looking where animals migrate, where you find them, so you wouldn't interfere and unnecessarily kill marine life. Do you work with marine scientists or other scientists in establishing these migrations, or how does it work?
Yes, absolutely. So as we're part of course, Florida Atlantic University, and Florida Atlantic University has many strengths on marine science. We try to engage the scientists that are experts in the field, world-renowned scientists in the field. To give you an example, so generally, the regulatory agencies, when they're looking at approving projects that would go out into the field, start with what type of habitat is available, and then move on to what kind of species or animals of concern are highly likely to be affected potentially by the technology that's in the water. So with respect to habitat, at least offshore Southeast Florida, we have a very sensitive reef system, including ancient deep water coral reefs. Harbor Branch Oceanographic Institute scientists at FAU are world experts in surveying and understanding these resources. So we've worked with them in many of the preliminary geophysical surveys that we've had to do to be able to determine where would be the best place to put equipment. And obviously the strategy there is avoidance. In terms of the animals, the regulatory agencies look at species that are a priority, so that are regulated. And in our case, off Southeast Florida, the two primary types of species are sea turtles and marine mammals, both of which are very much studied by FAU scientists here. So we've engaged with them to better understand exactly where are these animals during the year, what do they do when they're in these various places that are offshore, can we avoid them, can we find other forms of mitigation, how do they actually interact with equipment once the equipment's in the water. And the regulatory agencies use a strategy called adaptive management, where they allow small, low-risk projects in the very beginning to get into the water so that at the same time, you can also then observe exactly how the wildlife interacts with it with lower risk to the populations themselves. So yes, we do work with as many of the researchers here at FAU as possible, but we also have an extensive network of other universities that we work with around the country and the world to try to share knowledge, share results, and to find ways to expedite providing information to the regulatory agencies.
Great. Okay, here's a question from our audience. You mentioned the 4 to 6 gigawatts earlier, and the question here is, where did the potential 4 to 6 gigawatt generation figure come from? And what was that for a single generation device or a series of devices?
Very good question. So when the U.S. Department of Energy looks at how it evaluates the opportunities for various renewables, not just marine renewables, but wind and solar as well, they organize studies that will take a look at exactly what is available. And they have different classes of understanding the resource. So at the very lowest level, we have what's called the theoretical resource. And that's related to how much energy is actually present in the natural environment and how much of it is moving by that's available, right? So that's called the theoretical resource. Moving from there, now you start to incorporate limitations that technology might have, for example. So if you were to place a turbine, which has natural efficiencies and reduced efficiencies in our physical world, how much energy could then practically extract from that, right? And they have another classification called technically extractable. So now this takes into account all of the socioeconomic aspects as well. The study in 2013 that generated that number are actually from technically extractable resources. So that means that if you were to place as many turbines as you could possibly install in the Florida Straits to capture all of the Gulf Stream flow that's available, you could generate approximately 4 to 6 terawatt hours per year. The study, though, also takes into account at what point does the natural resource itself try to either avoid the equipment rather than moving through it and exchange energy with it, or do some other oceanographic things that would affect how much you could ultimately extract. So that number is actually very close to what our practical natural number maximum is in order to be able to tap into the Gulf Stream for this power.
Very interesting. So we coming back to the use of currents, and a very interesting question is here, could you use rivers or the current in rivers rather than the ocean?
Yes, and as one of the companies that I highlighted to show the advances that we've made in the US generally in the marine energy sector, one of the companies, the Ocean Renewable Power Company in Maine, has done exactly that. So they realized that rivers ebb and flow, but they're more closely related to the rivers in the ocean currents. So why not try to, instead of damming rivers like we've done historically, let's place the same equipment, albeit at a smaller size and maybe with less units because there's not as much available space. How can we generate electricity that way? So they've done this in Alaska. And the reason they've done this in Alaska is severalfold. One, the resource is high in Alaska in terms of rivers with all the glacial melt that increases the flow in the rivers. But in addition to that, the communities that live there are also paying very high prices for the diesel energy that they currently use. And the marine energy systems that they've placed in Igiagik, in a river, have been able to mostly offset those diesel prices. So that's a very good question. And many of these technologies also cross over. Anywhere that you could find a fluid flow, water that's flowing by, you could adapt the same technologies to either one of those environments. That's a very good question.
So you mentioned some other companies and you just mentioned Alaska. Are there other parts of either our country or around the world that have developed similar technologies and are maybe further ahead of us that we could learn from?
Yes, absolutely. So in Europe, projects like this started to get funding about a decade before the US really started to earnestly invest in them. So we've seen in the UK especially that the technologies, the resources have all moved towards full scale, full commercial scale individual units. And they're now trying to build these units in tidal. Of course, they don't have ocean currents, in tidal and wave in order to be able to better understand and help the entire industry out to better understand the reliability of these systems. The ocean is a very unforgiving, very harsh place to place equipment, right? And if we're going to amortize the costs of these capital investments over the periods of what utilities call power purchase agreements, we need to be able to have this equipment last long enough, 20-year periods, to be able to recover funds for the investors and project developers. What the UK has not done that I do think the US has a head start doing is better understanding the environmental impacts or the large and small scale potential environmental impacts. The US took it slower, but we're catching up. And I think that now the playing field is getting quite level. The US Department of Energy has significantly increased the amount of investments the past few years. Some due in part to our efforts to help try to get our federal representatives to understand how valuable and important these projects could be. But the office has also finally been approved as a formal office in the Energy Efficiency Agency in DOE. And so we're now seeing levels of funding around 120, 130 plus millions of dollars annually, which will help us to even more close the gap with our European counterparts. In other parts of the world, we've also seen advancements in Asia and in China specifically. There have been significant investments, but I think we're all starting to now kind of catch up to each other and work together to sort of a rising tide raises all ships, if the metaphor could be appropriate for this domain.
Okay, here's a very interesting follow-up question from one of our attendees. How soon could you have this all done if investment and legislation issues were solved? There's a follow-up question, but let's answer that one first.
So the challenges for us are making sure that the funds are available for the projects that are needed to fit into our strategies. In this way, we can build a long-term program that allows us to anticipate the needs of the industry, anticipate the needs of regulators, and move forward. As university research often tends to be, there are several years that are generally required to get some meaningful results, and then test those results in peer-reviewed publications, for example. So we're always a little bit ahead of the game. We're trying to be a little bit ahead of the game. And so funding and the vision from our legislators is necessary in order to be able to provide those funds when they're needed to accelerate the projects. I think we're at a point now where our partners at the U.S. Department of Energy are looking at it the same way. I think that the primary financial needs are starting to be met. I'm very optimistic about our future there. From a regulatory point of view, we've worked with these agencies, both at the state, local, and at the federal levels. And we have established the basic framework that's needed for commercial projects to start getting in the water. Companies like those that I highlighted in the tidal regimes have started to sort of be beta testers, right? They've tested the waters, also pun intended, about how exactly a company would navigate through these processes. And I think it's very encouraging. I think that as more companies begin to test these processes, the regulatory agencies will have opportunities to further refine and optimize them as well. I think our resource managers are little by little becoming far more comfortable with the projects and the data that's supported to show that the projects are sustainable and responsible. And so continued funding in those sort of three legs of the stool will help us to accelerate. The key point, though, and I think this is important to understand, is that ultimately the private investment community as well as the industry itself need to step up and make it a self-supporting, viable industry and a marketplace. While the public funds help us to establish and provide the tools and mechanisms to move forward for the industry, ultimately the industry starts to have to pick up the slack and balance the amount of public funds that are there to move commercial projects forward. So we're very optimistic about some of those trends and some of those indicators. We think that the public funds will continue to be available. And we have very good working relationships, especially with Florida delegations at the Florida level, the federal level, to keep these projects moving forward.
Maybe to add to this, as you can tell, first of all, it's very complex to run a project like this. But then also, if you're relying primarily on federal funds and in particular grants, it takes a long time, and the project managers are spending the majority of their time, I would say 99% of their time, trying to get funds rather than accelerating the project forward. And it takes multiple years until funding actually comes in from the time you're actually applying towards when you're actually getting the funds. So all this is a holdup. So private investment would be much faster in that regard when compared to federal funding. Okay, let's go to the next question here. Is there a chance that the power generated could be transmitted elsewhere?
Oh, that's a very good question. So, of course, I've spent most of my discussion today focused on utility scale. So this is producing power that's meaningful for our communities. There are efforts underway, driven in large part by the U.S. Department of Energy, that recognize that, hey, wait a minute, when we have small scale equipment, generation equipment like turbines or wave energy devices that are being built and then tested but aren't really quite the commercial scale yet, maybe those have applications in these other uses. So we do have the opportunity to try to power users that might be there where the currents are. So a few examples come to mind, and this is something that we've been working with our partner Lake Worth Beach to help establish, because testing and powering these systems is a little bit more of a baby step. It's not so far offshore, it's in shallower water, and can be more easily connected to the grid. So a few examples. The power that's generated offshore could be used for offshore aquaculture. There are power demands for offshore aquaculture. They could also be used for several Department of Defense applications. Our Department of Defense operates autonomous vehicles that move around our oceans and perform several observation and other tasks in our oceans. These need to be repowered. So rather than having to have crews that go out, recover the equipment, exchange equipment, repower the equipment, you can have underwater stations that are connected to these turbines that provide power at the point of generation, rather than having to bring cables from shore to be able to repower these systems. Another very interesting application that we're looking at right now is offshore data centers. So it turns out that Google, Amazon, and some of these other large data center and cloud computing providers have these onshore buildings that house thousands of servers. And these servers require cooling, and of course they require a lot of power. If you can find a way to package these servers under the water, you gain sort of a twofold benefit. The first is that the water, which is cooler than the air inside the server rooms, can help to bring down the electricity usage demands. The majority of the demands for electricity usage for servers are to keep them cool. So if we can use the water to cool them down to begin with, we can also help to power the remaining demands from the energy that's generated right there in the ocean where they are. So we're looking at also providing opportunities for our turbine developers, for example, to link up with these other interests and to work out some of the compatibility and integration challenges that are present to make these a commercial reality. And it also help our turbine companies to potentially get a source of revenue before they've reached their sort of final commercial utility scale needs, which are far more capital intensive. So we're very optimistic about these as well. The US Department of Energy has been promoting this and developing and investing in it for several years now. And of course, we intend to participate in that as well.
Great, very nice. You mentioned your collaboration with Lake Worth here on the East Coast. Here's another question on whether there are any initiatives, similar initiatives that could work on the West Coast of Florida, like the Gulf Coast.
That's a very interesting question. So if we're looking at taking advantage of the currents, the loop current, which is a part of the system for the Gulf Stream, is not generally found in the same place. And that's a very important aspect of trying to generate continuous electricity, both from the point of view of the utility, but also from the point of view of the project developer who wants a continuous revenue stream, not an intermittent revenue stream. So placing the same types of units in the Gulf of Mexico is possible, but potentially more challenging, potentially a technology that we could take advantage of once these other projects in the main currents reach these economies of scale, drive down the costs of the parts and the connection pieces and all of the electrical infrastructure that needs to be placed offshore in order to support the turbines. There have been some interesting projects in the Gulf of Mexico on offshore oil facilities as well. So, you know, obviously the engineers that work out there have noticed the currents that occasionally go by the platforms that they work on, and they've come up with some smaller scale systems that can help to supplement the power that the rigs themselves use, rather than relying on as much diesel fuel that needs to be brought to the platforms. So I think there are a few opportunities there. It's also been thought about to try to do wave energy systems. Unfortunately, the Gulf of Mexico generally doesn't have a high enough, from a utility point of view, energy climate that would encourage or enable projects of that scale to be useful. But we may also have applications like we've seen at these small scale systems that we've just talked about, where some of the offshore activities, ecotourism, for example, another example, may be able to take advantage of the lesser power that's available, maybe more intermittent. We've also seen cases where companies can sort of move around and mine the energy resources. This, of course, presents more technical challenges. Rather than placing a system in one location, you have to find a way of moving it around in order to be able to sort of follow the loop current as it moves around in the Gulf of Mexico. But all of these are possible, and they all become enabled by the research that we do here at FAU.
Thanks, Gabe. Somewhat related to that, you mentioned again Lake Worth, and the question here is whether, how often, how frequent do you need to have these kind of facilities, and how much area do you need to cover in order to provide power for example, for a city or for a county, for a state? How much area do you need to cover and to provide that kind of energy?
Yeah, so the answer to that very much depends on which technology or technologies would ultimately be selected for the power production. Some of the various approaches that I showed on one of the slides take up differing amounts of space. Some of them can be grouped together. Some of them need to stand alone. And generally, the Gulf Stream off the coast of Southeast Florida is found in about 1,000 feet of water or more, which means that any of the equipment that wants to take advantage of the higher energy potential near the surface needs to either fly like an underwater kite attached to the seafloor, or have a platform at the surface that could then put the equipment into the water below it. That naturally means that you need to space them apart. The types of moorings that you would use in order to be able to put them in place most often have some compliance, right? They can respond to a little bit of the motion. It's called a watch circle that the equipment would have as it moves around within the water column. This is also advantageous for the systems because then it can automate its ability to also search around in a smaller area where it might fly in order to be able to capture the energy there, best capture the most energy it can. So what we would look at would be which technology is being used. And remember, there may also be a hybrid of the technologies. Some of the technologies might be more appropriate for the edges of the Gulf Stream, and some might be appropriate for the center of the Gulf Stream where it's more continuous and larger area. You would ultimately try to find ways, just like wind farms, to be able to space them out. So maybe a few upstream, wait until the wakes dissipate and the current recollects, and then install another group of turbines behind that, and then moving up the shore. We have other limitations that would potentially limit the amount of area that you could try to use. Which is how far is it to shore to deliver that power? As the current moves away from the state of Florida past Palm Beach County, it gets further and further offshore, which means that the generation cables that need to be installed increase in complexity, in cost, in size, which may also limit the amount of projects in the area that the projects could consume. We're very optimistic about opportunities. The initial partnership with the city of Lake Worth Beach is to establish a offshore test facility. So this would accommodate 5 to 10 turbines at several different locations that could be installed either as groups of equipment of the same kind, or variable groups, or individual units. And this would allow companies the opportunity to both connect back into a grid and better understand how their equipment puts power back onto the grid and conditions it for the grid and meets the grid code requirements. But also it gives them an opportunity to leave equipment for longer periods of time, which would then help them better to understand the reliability and the costs associated with keeping the equipment in the water for long periods of time. So unfortunately, there's not a really good one-size-fits-all answer for that particular question. And it really depends on the projects that are selected and how those projects are selected.
And as you can tell, it's very complex. It's all the parameters that have to be taken into account. Different question. Do you know if FAU is still studying ocean thermal energy?
Yes. So when our center was first established, we were focused on 2 of the marine renewables in our backyard. And in the very beginning of my presentation, I noted that there are two different forms of energy that can be found in the ocean. One is the potential energy, which is the gradients. So ocean thermal energy conversion, while not efficient, really has the opportunity to take advantage of where most of the energy in the oceans is stored. The temperature difference between the warm surface water and the cold bottom water, especially in the tropical oceans. So in the very early years of our program, we worked with several industry and public sponsors, industry like the Lockheed Martin, for example, who were looking to develop technologies that could take advantage of that. This is basically a process that would take cold bottom water, move it up to the surface, use that to cool down a liquid, so like ammonia, that has a phase change. It changes from a liquid to a gas that would then power a turbine, for example. And the warm surface water would sort of have the opposite effect, and it would recycle this way. The efficiencies aren't high, but the opportunities and the amount of energy that's available are vast. So there has been a little bit of a diversion from the US from looking at OTEC projects. The project that Lockheed was working on with the Navy finished and wasn't restarted. But many of those technology innovations were then picked up in other parts of the world. And I think that's starting to come back to the US. The Department of Energy has now officially included it in its projects that it's looking to invest in from the Water Power Office. And we're very optimistic to use some of the data that we collected to better show that, hey, off of our coast, we can actually find that temperature difference that we need in a lot less than 3,000 feet of water, in about 1,000 feet of water, which significantly decreases the technology challenges. So we would love to continue to work on those. But as you mentioned, a lot of the work that we do is dependent on the sponsor's needs and the sponsor's direction of where we go. We try to build a strategic vision for it and piece it together along the way, but we're very much dependent on that. We would love to get back into the OTEC research.
And we do have a question here, how private industry can help. I encourage you to reach out to Gabriel Alsenas directly, either through the email that was shown in the presentation, or you can contact me and I'll get you in touch. We're almost out of time, Gabe. I know we have a few more questions here. We will have you answer the remaining ones offline and post the answers on our website. Now I'm going to ask a last question. What is your favorite aspect of doing research?
Which is why I'm here outside today. So my favorite aspect is actually getting to do this hands-on. I'm trained as an ocean engineer, and working in the ocean and developing and testing systems in the ocean are my favorite part, of course. All of the things that we do to help ensure that funds are available, that our partners are engaged, are very important, and I enjoy that as well. But the most important, sorry, not the most important, the most enjoyable piece of it for me is actually getting offshore and being able to get wet with our projects. So.
Great. Thank you very much, Gabe. I really appreciate you taking the time out of, wherever you are in the field to talk with us today. Thank you very much for calling in, everybody. We will hopefully see you next week again for another Research in Action. We will post the remaining answers with a recording of this presentation on our website, FAU Research in Action. Thank you very much. Have a great rest of your day.
Thank you.